This video is on hydrodynamic instabilities, and it's going to take a somewhat different form to the other videos in this series, in that we're just going to work through one relatively lengthy, relatively complicated problem to reproduce a stability calculation that's representative of other stability calculations you can expect to see in fluid mechanics. And the instability we're going to focus on is actually pictured here. It's called the Kelvin-Helmholtz instability. And the Kelvin-Helmholtz instability arises when you've got a shear between two layers of fluid that are moving at different velocities. So what we've got pictured here in the atmosphere is, you can imagine there's two layers of fluid here with an interface roughly with this dotted line that I'm drawing, and we've got one velocity here, u1, we've got one velocity here, u2, and u1 does not equal u2, so we get an instability. And the instability changes the position of the interface between the two layers, and it folds up and forms these ripples. So can we analyse this in a simplified fluid system? And what we'll do is we'll talk through the stability calculation that gets you the growth rate of this instability, and it will reflect how you might approach other stability problems that you'll see in continuing mechanics courses. So let's draw out a simplified physical setup here. So here's a boundary which I will denote z equals 0 between two semi-infinite layers of fluid. They've both got the same density, rho, and the upper fluid moves along with velocity u1 in this direction, whilst the lower fluid moves along with velocity u2 in this direction. We'll have axes x in this direction and z in this direction, so all the flow is in the x direction. And so in the base state, this interface is purely planar, and the velocity in the top layer is just u1 x hat, and the velocity in the lower layer is just u2 x hat. Now what we want to do is we want to perturb the interface here with a sinusoidal perturbation, and this is standard for normal mode analysis. So normal mode analysis is we look for normal modes with a certain wave number. This compare this with, say, Fourier analysis. So we're looking for Fourier modes, implicitly Fourier transforming the whole system. So we want the new interface to be eta, which is equal to some constant times e to the I kx plus sigma t. Now this k here is a wave number for the instability, and this sigma is a growth rate. If sigma is positive, then this new perturbed interface is going to grow exponentially. If it's negative, it's going to decay exponentially. So if it's positive, sigma greater than 0 implies instability. And more specifically, we can work out sigma as a function of k to get the growth rate of a certain mode. With the normal mode with wave number k. So in this specific problem, like I've said before, we'll just do another sketch to make things especially clear. We're going to perturb the interface to get this sinusoidal form. Now I should probably say we're implicitly taking the real part here, so you can think of this as a cosine if you like, but it's easier to work in complex variable forms here. So this is the perturbed interface, z is eta hat e to the I kx plus sigma t, and this is the original interface, z equals 0. And up here the velocity is u1, down here the velocity is u2. Now in order to accommodate this perturbed interface, we're going to have to perturb the velocity fields. And so we'll take u1 to be u1 x hat plus u1 tilde, and u2 x hat plus u2 tilde in the lower layer. Okay, so key assumptions that we're going to make here to make our life a lot easier is we're going to assume that the flow is inviscid. And notice in the base state there's no vorticity. And if you go back to the vorticity equation, you can see that if the flow is initially irrotational, it remains irrotational unless there's a body force acting on it, or we've got viscous effects leading to the generation of vorticity. We've got neither of those things, so the flow is irrotational for all time. Okay, that means that our perturbation velocities can be written in the form of velocity potentials. So we'll call these grad phi 1 and u2 tilde is equal to grad phi 2. Okay, now let's write down some governing equations. So the governing equation for this just comes from incompressibility, and because div u is 0, that implies that del squared of these potentials is 0. So div u equals 0. Well, the base state velocity field trivially satisfies being divergence free, but this just gives del squared phi I equals 0 for I equals 1 and 2. Now we're going to make the same, in order to apply our boundary conditions later on, we've got to assume the same x and time structure for these velocity potentials. So we're going to make the assumption, as is standard in normal mode analysis, that phi I is equal to phi I hat as a function of z, e to the ikx plus sigma t, and that therefore implies that phi I double prime hat minus k squared phi I hat equals 0 when you plug this in to Laplace's equation. So phi 1 is equal to a e or phi I. Oh, sorry, let's just simplify this a little bit more. Phi I is therefore just going to be proportional to e to the plus or minus kz. But we want decay away from the interface. At infinity, we don't want this small perturbation to have any role. So that implies that phi 1 has got to take the form ae to the minus kz, and phi 2 is equal to be to the kz. We'll assume without loss of generality that k is positive. So both of these decay exponentially away from the interface. Okay, so we've got the forms of our eigenfunctions there. Let's think about some more boundary conditions, instead ones that can be applied at the interface. As usual, these can be separated into kinematic and dynamic conditions, as we've seen before in the introductory fluid mechanics section. So let's start by thinking about the kinematic boundary condition. So if we apply the kinematic boundary condition, that's just going to be the material derivative of the interface is equal to u dot z hat on z equals eta. Basically, the vertical velocity of the interface has got to match the vertical velocity of the fluid, somewhat obviously because u dot n equals u dot n, as we saw in one of the earlier sections. So if we write this out in full, taking out the form that we know eta has, this gives us sigma eta hat e to the ikx plus sigma t plus u dot grad eta is equal to, well, we'll just call it v in this case. So we'll say that u is equal to uv. Okay, what's this term here? Well, because we know that eta is eta hat e to the ikx plus sigma t, we can go one step further and say sigma eta e to the ikx plus sigma t plus u times ik eta hat e to the ikx plus sigma t is equal to v, where u and v are evaluated at z equals eta. But we're carrying out a linear stability analysis, so we want to linearize this. So we'll come back to what that means in a second, but let's just substitute in for u and v in the two regimes. So above, so maybe we'll come back to the term linearize in a second. So in 1, we have sigma eta hat e to the ikx plus sigma t plus u1 plus d phi 1 by dx ik eta hat e to the ikx plus sigma t is equal to d phi 1 by dz, again at z equals eta, and we also have in 2 this expression. Just the same thing, everything replaced with a 2. It seems a bit tedious to write it out, really. Okay, let's talk about linearization. So all of the perturbation quantities are assumed to be small. So we ignore products of small quantities. So eta hat is small, as is phi in these cases. Perturbation quantities are small. Therefore we linearize them. And so that gets rid of this term here and this term here. Okay, so what do these kinematic boundary conditions finally give us? Well, everything is proportional to e to the ikx plus sigma t, thankfully, and we just end up with sigma eta hat plus ik u1 eta hat is equal to minus ak. The other thing that we do is we evaluate on z equals 0, and that's also from the linearization. Because if you take a Taylor series of these exponentials, we just want the leading order term, which is at z equals 0, and not any contributions from z equals eta. So 1, this comes from 1, and we also then have sigma eta hat plus ik u2 eta hat is equal to bk, and this comes from 2. Just subbing in the form for sigmas that we derived up here. Sorry, these should be hats. Okay, right, with these boundary conditions, we can therefore calculate what A and B are. A is equal to minus sigma plus ik u1 over k times eta hat, and B is equal to sigma plus ik u2 over k eta hat. Okay, so that's our kinematic boundary condition. The other boundary condition we need to concern ourselves with is a dynamic boundary condition. And so the dynamic boundary condition in this case, we call it BC, yeah we did. The dynamic boundary condition in this case comes from matching pressure across the interface. So let's write down the full dynamic boundary condition before we do any linearization. And if you recall Bernoulli for an unsteady but irrotational flow, we notice that this is what we get in region 1. E to the ikx plus sigma t, this is our potential energy, is equal to some function of time minus the pressure. Okay, this is in region 1. Let's see what u1 squared is. Well, it's going to be u1 plus ika e to the ikx plus sigma t squared plus times, obviously we've also got the e to the minus kz squared plus well, this is on z equals eta, sorry, plus also then just minus ka e to the ikx plus sigma t minus kz squared. So let's start linearizing this again, and the only terms that remain when we linearize are u1 squared plus 2 u1 aik e to the ikx plus sigma t. And again, linearizing e to the minus kz on z equals eta, well, this will be doubly small if we take any contributions from eta, so we just evaluate it on z equals 0. So this is when linearized. Okay, let's go back to this equation here, and we're just left with rho d phi 1 by dt linearized onto z equals 0 is sigma times, where are we, sigma a e to the ikx plus sigma t plus 1/2 u1 squared plus u1 a ik e to the ikx plus sigma t plus g eta hat e to the ikx plus sigma t is equal to f1 of t plus p. Okay, so let's move some more things over. We also implicitly assume that our perturbation pressure is proportional to e to the ikx plus sigma t, because all perturbation quantities are proportional to this. So let's move this term over, and we're just left with, move p over to the left hand side and move this u1 squared over to the right hand side, and we're left with stuff proportional to e to the ikx plus sigma t is equal to f1 of t plus 1/2 rho u1 squared. But this here is just a function of time. It has no x dependence, so it therefore equals 0. This is very handy because it just means that we can write now rho sigma a plus u1 aik plus g eta hat is equal to p. And we can do exactly the same thing in the case of the second region, and we get rho sigma b plus IKU2b plus g eta hat is equal to p analogously. But pressure matches across the interface, so these two sides are equal to one another, and we're just left with sigma plus IKU1 a is equal to sigma plus IKU2b. Alright, so this result here gets us pretty close to our final result. Remember what A and B are? Well, this can then, so we substitute in from the kinematic boundary condition for A and B, and that gives us an expression that is just sigma plus IKU1 squared plus sigma plus IKU2 squared is equal to 0. So this is a quadratic, and we can solve this quadratic with the quadratic formula. I'm not going to actually solve it here because I've quite helpfully got it written down next to me. And sigma is just equal to minus IK over 2 times U1 plus U2 plus or minus K over 2 U1 minus U2. Okay, so irrespective of, provided that, jumping all over the place, provided that U1 does not equal U2, there exists a sigma with the real part of sigma greater than 0. That implies instability. And the growth rate increases for higher and higher wave numbers, and also is higher for a greater contrast between the two velocities, which is what you'd expect. You'd expect these ripples to grow more rapidly in cases where there's a lot of shear, i.e. there's a really, really marked step change in the horizontal velocity, or when k is really, really small, you have k is really, really big, you have really, really small wavelength ripples, which you'd expect might grow an awful lot faster. So that's an example of how we carry out a stability calculation. You can do a similar thing to calculate other instabilities, like the Rayleigh-Taylor instability. That will be covered in the Part 1b notes if you go and look up the Dexter notes that I've referenced in other ones of these videos. But here's a kind of fully worked example of how to get the growth rate for a given instability by using potential flow theory and solving for a dispersion relation.